Okay, today we're happy to have the illustrious David E. Kaplan from Johns Hopkins University, who will tell us about shadow matter.
Yeah, much better. Hey, everybody. Yes, please interrupt. This is just a long standing set of ideas and thoughts to understand, in a sense, the a little bit of looseness within gauge theories and gravity, and how maybe best to quantize them or to look for new phenomenon. And sort of blanket describe this as shadow matter. And yes, okay, preamble. Just to remind you that the classical equations of motion, of course, can be derived from an action, an Lagrangian, and we can construct a Hamiltonian out of that classical action. And the Hamiltonian becomes a starting point of how we define a quantum theory that we might be interested in. And we start from the classical theory because we'd like the quantum theory to look like the classical theory in a classical limit, say for coherent states or for states with very small uncertainty for the observables we care about. So to get to the classical theory, the reason that quantum theory generates a classical theory is Ehrenfest's theorem in quantum mechanics, which is simply the fact that if you have conjugate variables like x and p, then the equations of motion come directly from a single first order differential equation, which is the Schrödinger equation. And then if you treat either those x's and p's as expectation values in the state of x and p, or if you're in the Heisenberg picture and these are time-dependent operators, then the equations of motion follow directly from the Schrödinger equation. You take a time derivative and of one operator and you get variation in the Hamiltonian with respect to the other. And so we get, as you see, F equals ma effectively from a Hamiltonian, which came from a classical language, but where we simply put hats on everybody. So that's the theme. We choose a Hamiltonian to get the classical equations we want so that the classical limit looks correct. Now, there are cases where the Hamiltonian isn't built in such a clean way. For example, if you have some conjugate parameters, one of which doesn't appear in the Hamiltonian, then you have these free directions. So the simplest example, of course, is where if you have two particles, let's say both of mass m, and the potential is only the interaction term between them, and it depends on the difference in the coordinate of particle 1 and 2, then you can, of course, rewrite the Hamiltonian in the center of mass frame, and you get two conjugate momenta, but only one coordinate that appears. And so there's in a sense, a useless parameter, which is the overall momentum of the system. And you can think of the state of the system as being in some, for example, it could be in some momentum eigenstate of that total momentum, but nothing there allows us to measure that total momentum. So you could think of the entire Hilbert space as containing the set of all possible total momentum of the system, but these are super selection sectors in the sense of you can't get from one to the other. P, capital P, commutes with the Hamiltonian, so whatever you fix P to be at the beginning will be P forever, the total momentum. Now you can decide that the full physical quantum state of the system is one where the total P is zero, where the total P is non-zero, but an eigenstate of the P operator. Or even you could decide that the initial state of the system is an expectation value of that P operator, and whose average then or expectation is some value, capital P. But it doesn't matter and also doesn't physically matter. You could also have the possibility that P still commutes with the Hamiltonian, but maybe its value does matter in the sense of the potential associated with dynamical quantities. So let's say there's a potential function for that relative coordinate q, but it depends on the value of capital P. And so still capital P commutes with the Hamiltonian. And the physical state of the system could be one in which the total momentum is zero or equal to some capital P, or maybe again, you're in some quantum state which is a linear combination of different eigenstates of capital P, and the expectation value would be some value P. You could imagine even being in a coherent state of total momenta. And then when you make a measurement, when you're in, you are checking what the value of that potential is, V, total V of Q, which is the sum of those two terms. In a sense, you're measuring what superselection sector you're in. And if it's in a linear combination, that measurement entangles you with the outcome.
Sorry, can I ask a question?
Yeah, yeah, sure.
So if you were to put the hats on your Hamiltonian, would the Q inside V bar have a hat or not?
Yes, the Q, oh, yeah, I'm sorry. All of those, I was sloppy with notation. So the Hamiltonian, all the P's and Q's have hats on them in the Hamiltonian.
That is an operator. Okay.
Yeah, that's right. That's right.
Okay. Thanks.
So let's take that story and bring it to electromagnetism. And of course, the way we think of electromagnetism is either with Maxwell's equations or we start with a classical action. And from the classical action, we demand that variations with respect to all four vector fields, A0 and A vector, vanish. And those variations with respect to A0 give you Gauss's law, and with respect to AI gives you Ampere's law, those three equations. Now, if you then want to convert to a Hamiltonian, you do it sort of strictly in the standard classical language. You find a conjugate momentum for the A vector, but there is no conjugate momentum for A0 because, of course, A0 dot doesn't appear in the action. And so now you have some freedom to decide what you mean either by pi 0 or A0. The Hamiltonian then is going to take this form. A0 will appear just by fiat because there's no conjugate momentum necessarily that allows you to remove A0 dot. There is no A0 dot. But we know from the classical story that there is a gauge symmetry, and the gauge symmetry suggests that values of the classical fields have some gauge redundancy. And so we know from, of course, years of effort in quantum field theory that you can simply choose a gauge and you expect that the physical observables in your system will be gauge invariant or could be defined as gauge invariant. And so we make a choice to simplify this Hamiltonian. For example, we can choose the Weyl gauge where A0 is equal to 0. And now the nice thing about the Weyl gauge is that the commutators you define can be the simple canonical commutators between A vector and E, the electric field, which is in fact the conjugate variable for A. And when you do that, you get the equations of motion. And the equations of motion you get are just Ampere's law. Now, Ampere's law is a dynamical equation in that it's a equation for the time derivative of the electric field, or the second time derivative of the vector field. Gauss's law does not come out of this. We've removed A0, and Gauss's law, in fact, is not a dynamical equation anyway. In terms of the conjugate variables, it is a constraint equation on the electric field. It's just that the longitudinal part of the electric field attaches itself to charges. And so the classic way to implement this is to first note that Gauss's law as an operator commutes with the Hamiltonian. And because of that, you can simply require that the physical states obey Gauss's law. In the free theory, you're just saying that the physical states are in fact eigenstates of the longitudinal part of the electric field. So they're not in, say, Fock space states, they're in exact eigenstates of E longitudinal. And you can choose that, and that will be true for all time because G and H commute, and therefore this eigenvalue is time independent. So going by the same attitude as before, we can also ask what happens if physical states are not required to satisfy Gauss's law, but to satisfy some eigenvalue equation, such that G acting on the state produces some function of just space, not time, since we want this to be time independent and must be by the fact that it commutes with the Hamiltonian. You can even choose states where they're not eigenstates of G, but the expectation value of G vanishes, or the expectation value of G is some function. If you have that, then you see that the expectation value of Gauss's law minus this function is equal to 0, which is just to say that this is equivalent to inserting a classical background charge density. Not surprising, this theory can be quantized as easily. It just looks as if there's a static background charge. Okay,
Question.
yeah, go ahead.
So if you did this with a path integral rather than with canonical quantization,
Yeah,
there's this theorem by Hallowell and Hartle that any state that's generated by the path integral is annihilated by Gauss's law. And that's actually easy to prove by just changing variables
sure.
in the path
Yeah,
integral. So
yeah,
this
so this is
something different from path integral that's inequivalent to path integral quantization.
so this is what's happening in that language. The path integral, remember, is simply a solution to a differential equation, which is the Schrödinger equation. And the path integral being a solution to a differential equation includes a choice of initial conditions. And so the point is that if you wanted to take this theory with either an explicit violation of Gauss's law, then you've chosen the set of states that you're going to include in the path integral. So the way you get from, say, Weyl gauge of the Hamiltonian to the path integral is you include a projection operator on the states that forces you to conserve Gauss's law. And the way that's then imposed in the path integral is that you've reintroduced A0 as a Lagrange multiplier. And that Lagrange multiplier then multiplies exactly Gauss's law as it appears here. So you can impose it in that way, and then, of course, the path integral you get out, the action is Lorentz invariant. Now, if you instead decided that you were going to live in states that had an explicit violation, they were eigenstates of G, but with some classical function, rho of x, then when you derive the path integral, what you discover is this term appears in the path integral as A0 times rho of x. It looks like an explicit violation of Lorentz invariance or translation invariance because you've simply put an explicit background classical source term in the path integral. So in that path integral, Gauss's law is in fact preserved, if you include this additional charge density. Now you have another option, which is that you can decide you're not imposing anything about Gauss's law. You're going to leave the path integral, or sorry, the Hamiltonian in Weyl gauge, and then you're going to derive a path integral. And in that language, you don't include any sort of requirement that the states that you insert preserve Gauss's law. And if you do that, you end up with a path integral which looks manifestly not Lorentz invariant, doesn't have A0 in it. But if you calculate the propagator, what you find is a normal propagator for the photon with two polarizations, but with one extra pole. There's a 1 over energy pole. So at energy equals 0, there's another pole to the propagator. But once you choose initial states and ask how initial states propagate for physical photons and say charged particles, you discover that pole does not appear in any S matrix calculation. And so in that sense, yes, the path integral with a fully Lorentz invariant action without any source term like this looks to satisfy Gauss's law. And that's simply because you've made a choice about the initial conditions. Or you've simply decided that these states that could be in the Hilbert space don't exist in the Hilbert space, or that we're keeping ourselves within the superselection sector for which Gauss's law is preserved. And then, of course, the path integral will reproduce that. But you've already made that decision once you've constructed that path integral. Does that make sense?
I'll have to think about it, but So you're explicitly violating gauge invariance, right?
By choosing a Hamiltonian in a particular gauge, I've chosen something where part of the gauge is being fixed. And then the remaining spatial gauge transformations, the Gauss's law operator is in fact the generator of that remaining gauge symmetry. So, but yes, I've chosen I could do something more formal, and I could choose a Hamiltonian where I add a bunch of ghosts and I force it to be a BRST invariant theory. But I find it a simpler language is just to choose a gauge for the Hamiltonian and then generate the path integral from there.
Like choose a gauge for the Hamiltonian and then require that only gauge transformations that preserve that gauge are allowed in the path integral.
That's right.
So that is breaking gauge invariance. If you're saying
Uh,
you're integrating over a
I mean,
set of field, but you are not allowed to make a change of variables that's equivalent to a full gauge transformation. That's
I mean, at the end of the day, for this thing, you could just say that you're choosing a reference frame and
Right.
choosing a background J0, which in ENM is a gauge invariant statement, so the current is gauge invariant, and that you're just quantizing in the background of that. So that is an equivalent language to all of this, all of this.
Yeah.
okay, so then
You-
you're
So in
explicitly
that,
breaking Lorentz
you're
invariance.
explicitly breaking Lorentz invariance by
That's right.
including a non-dynamical background charge density.
That's right.
Okay,
So this of course lives in QED. I can have some charge density which is in some very classical state. Let's say I have some scalar field which is charge, and I can take a limit where the amplitude of that scalar field is very large, and the coupling of that scalar field goes to zero, but keep the charge density finite and fixed. And so that's a fully gauge invariant QED, scalar QED, and there's a limit where it looks like this. But here I'm just doing something sort of dumber, which is to say if I take the language of the Hamiltonian in a particular gauge choice, what it looks like is that these are a set of states that are available in the Hilbert space. And there is one Lorentz invariant vacuum state where the longitudinal part of the electric field is zero, but there are all these other states. And those states are non-dynamical parts of the electric field, as opposed to the transverse or the photons, which are dynamical, which again, like our universe, you can choose a rest frame, turn on all those states, and start with an initial condition where they do dynamical things. If you turn this on, it's non-dynamical. But it's a limit of QED. Okay. Let me go to a toy model of gravity, so-called mini superspace. So this is just to get a taste of the gravitational version of this, which is, let's imagine a metric which doesn't depend on space, only depends on time. This is known as the mini superspace metric, where it's basically an FRW type of metric where there's a scale factor A of t, and I leave an n of t, the lapse, which allows me to leave time reparameterization invariance. Now, again, the classical action, the full GR classical action, Einstein-Hilbert action plus some boundary terms so you can get rid of second derivative terms, I can write, but then limit it to this metric. And then I can ask what the classical equations of motion are. One is a variation of the action with respect to n, the lapse, and the other with respect to a, the scale factor, and then the third with respect to any matter. In this case, let's say there's a scalar field with a canonical kinetic term. And the first two variations give me Friedmann's first and second equation times some overall factor that involves square root of g effectively. And then, of course, the matter equations of motion. So that's classical. And then you can decide that you want to impose, and this is really the take I'm starting from, which is say that the fundamental quantum theory is a theory with a Hamiltonian, and so I want to figure out again what is the Hamiltonian that generates the quantum theory with the nice classical limit. And so to get the classical Hamiltonian, I look for the conjugate momenta, and I again discover that one of the fields, in this case n, doesn't appear with the time derivative, and so there's no natural conjugate momentum to n. The matter fields have conjugate momenta, and so does the scale factor. And so I can build a Hamiltonian and forget the conjugate momentum to n. And when I do that, I discover something very simple, which is that the n dependence of the Hamiltonian simply appears out front. So there is a function of A and matter fields phi and their conjugates, and then there's an overall multiplication by n. Now, the reason that n should be there, or it makes sense, is the n is responsible for time reparameterization invariance. And since the Hamiltonian is going to appear in the Schrodinger equation, we see n appears exactly where it's supposed to, so that I can shift it to the other side, treat it as a function of time, and now this is a derivative with respect to the proper time. And so the n doesn't appear in the Hamiltonian, and n, like A0, is effectively a gauge choice. And so I will choose a simple gauge to define the observables, say n equals 1, and then I will again look for the classical limit of the Schrodinger equation and the quantum equations of motion. So just like in electromagnetism, I get the equations of motion from the Schrodinger equation by taking time derivatives of, say, in the Schrodinger picture, expectation values of the operators A and its conjugate. And the equation I get out is the second Friedmann equation. Now, the second Friedmann equation is a dynamical equation. It includes a time derivative of the conjugate momentum pi, which is why we get that equation out from Schrodinger equation. But the first Friedmann equation doesn't appear from the commutators. It doesn't come out of the Schrodinger equation. It is a constraint equation. And so the constraint equation comes from, well, the classical equation comes from the variation of the action with respect to n. But in fact, that equation is called the Hamiltonian constraint, that the Hamiltonian itself is required to vanish. That is what the first Friedmann equation is. It's h times, well, it's h equals to 0, and h is the first Friedmann equation times some overall factor of a's, the scale factor. And so the classic treatment of this is so-called Wheeler-DeWitt equation, where you demand that the physical states are annihilated by h. Now, the issue we have, or people have with this equation, is that you've removed effectively the Schrodinger equation. So the time evolution in your system does not come from the Schrodinger equation. And then the hope had been that living in this state, which the quantum state is simply a static thing, one can define a clock which is entangled with different timestamps of, say, the remaining part of the wave function. And this attempt to define that is something called the problem of time and quantum gravity. Now, there's a very simple fix to this, which is to simply say that the expectation value of the Hamiltonian is equal to 0. And part of the desire to do it in this way is to simply take the gravitational states, like cosmology, as coherent states. And coherent states are not eigenstates, of course, of the Hamiltonian. They're just classical states with very small uncertainty in the field values or in the wave function of those fields. And so if we say that the gravitational fields are a classical state of the metric operator, then we can also take this constraint and impose it simply an expectation value. Then we can extract the time evolution directly from these equations. So in that sense, then the first Friedmann equation, like the second Friedmann equation, is an expectation value equation. And for very classical states, these things are, to good approximation, just classical general relativity. Now, that also suggests that you could do other things with that expectation value. You could take the expectation value of the Hamiltonian and make it something which is non-zero but time independent, because of course a Hamiltonian commutes with itself. And if you do that, then you discover that the Friedmann equation gets modified by an overall constant. Or if you normalize it to the standard Friedmann equation, you have an additional term in the Friedmann equation that goes as c over a cubed, a being the scale factor. So it behaves as if there's another matter component, which is redshifting as 1 over a cubed. This is not a real matter component. This is just a statement about the non-dynamical parts of the metric. In this case, nothing is really that dynamical. But this is an extra source term then that affects how the universe expands, and it dies away as if there was some form of matter in the universe. So, just some points, which is to say that the equations that are modified are constraint equations and not the dynamical equations. One thing I didn't say here is they are dependent on the choice that I make in the Hamiltonian. So what I've done is I start with a Hamiltonian with a particular gauge, which is to say that things like a0 or the lapse function n, I've chosen to be essentially C number functions. In the a0 case, I took the trivial a0 equals 0. In the case of n, I simply took n is equal to 1. I could have chosen other gauges, something much more non-trivial, say where n itself is an operator that depends on the other operator in the equation, a. So n could have itself been dependent on the scale factor operator. There would still be then the same number of dynamical equations, the Friedmann equation, second Friedmann equation, but the constraint equation would not produce something like dark matter. In some cases, you could make the constraint equation be a source for a cosmological constant. And that is the Hamiltonian version of unimodular gravity. So I've made choices about what the constraint equations are, and then the dynamical equations are fixed by the Schrödinger equation. Now, in all of these cases, the extra source term that I've added are initial conditions. And except for the case of unimodular gravity, which I'm not talking about, inflation will redshift all of these things away. And we'll see later that even in the electromagnetic case, when you couple it to gravity, those source terms will redshift away. So inflation will remove all of these things. But we could ask, if there is not a period of inflation, if the early universe is dictated in some other way, would these initial conditions be interesting? So yeah, Marcus. Yeah.
Well, I was just wondering, in the case for electromagnetism, it seems much more physically transparent to me anyway, if you just write what the classical equations are, forget about all this Hamiltonian stuff, just
Yeah.
write the classical equations with the thing that you're doing, and you will look at them and you can just write them, and don't write them in this Hamiltonian thing, just write them in terms of the original variables. And you would find that, as you said, you're just including a background. Okay?
That's right.
So
That's right.
have you done that for gravity?
Yeah, in gravity, you are. I mean, we'll see it here. The simple term that I added for gravity looks like a pressureless dust.
No, but I mean, if you've written down the full equations for G mu nu, not the Friedmann equations for that.
Right.
Full
I'm about
equation.
to do. Yeah, I'm about to do that.
Okay.
Yeah, so I'll show you what the classical terms for gravity are. You're right. That quantum Hamiltonian stuff is just to motivate these source terms, but I'll write down what those source terms are for full GR. Okay, so for classical GR, there are 10 components of the metric. There are 4 gauge symmetries, and again, if you would want to go to the Hamiltonian language, you would describe these fields in terms of their conjugate momenta. And again, like in the other two cases, there are fields that don't have time derivatives on them in the action, and therefore there's no fixed way to define the conjugate momenta. And so these are the metric components that have at least one time index. So there are four of these fields, but you can still construct a Hamiltonian. This is this classic DeWitt construction. You can do it in terms of the spatial parts of the metric, and you can construct such a Hamiltonian, and you can choose a gauge. So again, the simplest gauge in this case, you don't have to, but
Can I get the meeting information? No.
the simplest gauge is synchronous gauge, where I take G00 to be -1. And now you can, again, generate the equations of motion, and the equations of motion you get are only the spatial equations of motion in this gauge. The Einstein tensor Gij, the spatial parts of it, equal 8 pi g Newton Tij. And the remaining equations are constraint equations that you naively impose on the theory. That includes the Hamiltonian constraint, which gives you the 0, component in the Einstein equations, and the momentum constraints, which are the 0I components. And again, the game we're playing is to add source terms for those. So those source terms, in principle, in general, are functions of space and time, but we will see that there are constraints on them. So in the case of both the mini superspace and electromagnetism, we knew what the constraints are on those source terms, namely that they were time independent. Here they're close to that, but we can calculate them classically.
Another question, sorry.
Yeah.
So synchronous gauge or Gaussian coordinates typically doesn't exist globally for solutions of the Einstein field equations.
Right.
But even if you restrict to solutions where it exists, you still have to choose an initial time slice. You
That's
have to
right.
choose a t=0. How do you do that?
So the way we're thinking about the quantum theory is that there is a manifold, and on that manifold we're placing the quantum operators, which are parameterized by points on that manifold. And then I'll choose a coordinate system on that manifold to better, describe these operators and how they evolve. But I've simply chosen a time. So in other words, I'm deciding that that manifold is going to be time cross a three-dimensional spatial manifold, and I'll define my quantum theory on that manifold.
But then if you choose a different time coordinate, do you have any proof that you would get the same quantum theory? I mean, classically, the invariance under choice of the initial time coordinate is guaranteed by the constraints, which you're no longer imposing.
Right.
So doesn't this mean that you actually have an infinite set of theories, one for each choice of t that you could make?
What I've done is I've decided from quantum field theory that time and space are distinct. And what I'm doing on that manifold where I've distinguished time and space is I've laid a set of operators and interactions in the Hamiltonian on top of that space. So you could, in some language, say that even in the case of electromagnetism, that Lorentz invariance is an accidental symmetry. That I'm saying that the Hamiltonian is a fundamental driver of time evolution in a Hilbert space, and I'm going to now describe a quantum field theory which luckily generates something which is Lorentz invariant. And in the same way, I'm going to choose a manifold that distinguishes time and space. I'm going to place my operators defined as functions of points on that manifold. And on some initial slice, defined by the time slice, I'm going to define my initial quantum state in the Hilbert space on that slice. and then let time evolve. And then in the classical limit, if I preserve everything, including the symmetries, and I set these source terms to 0 in expectation value, the classical theory will have a bigger emergent diffeomorphism symmetry that will allow me to do the transformations you're talking about. But it's an assumption that instead of saying GR is fundamental, what we're saying is the quantum field theory and the Hamiltonian language is the fundamental thing, and all of the additional local freedom in describing the theory in GR is emergent. It's the classical limit of this theory. And if we add source terms, those source terms are going to do things to the state and how the state evolves. Of course, the universe that we're in itself, it's reasonable to think that the quantum state we're in, of course, chooses a rest frame. It is decided that this is our rest frame and this system is going to evolve. But by putting in these source terms, we've also chose a rest frame, but we've put in non-dynamical, or let's say a little bit less dynamical sources for gravity.
And maybe at this point I could say, I mean, what my issue with this is, and it's based on what you just said.
Yeah,
you said that, oh, we can just have gauge symmetry be emergent, okay? So I don't have any problem with crazy arbitrary theories depending on crazy arbitrary functions or crazy arbitrary parameters. That's not a problem for me. Might be a problem for somebody else. Maybe it's a problem of motivation, but there's no fundamental problem with that.
Right.
There is, however, the thing is that if you don't, the thing is that if gauge invariance and the normal theory plays an extremely important role in getting rid of states that or configurations in the classical theory that have unbounded negative energy, and in the quantum theory have either unbounded negative energy or negative probability, which is probably even worse, right? And so once you start messing with gauge invariance, that isn't going to work anymore. And the U1 case, you can see that you're not really messing with gauge invariance, right? So that's why I wanted to see the classical equations of motion. If they're what they are in that box there, then I think there's a real problem. If this T mu nu SH is a fixed function of the space-time coordinates. Is that the
I mean, it will depend on, those are functions, H and P1, P2, P3, and this is also, of course, defined in synchronous in a particular gauge.
In a particular gauge, that's fine, but they're fixed functions of X of space-time. These H, P1, P2, P3, they could be sines and cosines. I could choose them, maybe subject to some conditions, but they're fixed. Is that correct?
Well, they're an initial condition in the same way that I can create it in a classical initial condition in gravity. I put a bunch of stuff in the universe and there'll be a density profile for that initial stuff. And then you can ask.
When you say they're an initial condition, you mean they don't depend on time?
They almost don't depend on time.
Almost. Okay. I don't know.
I'll show you those constraints.
Okay.
But
anyway, well, I'll just tell you what my issue is, because maybe I'm not understanding what you're saying. But the reason, the important feature that avoids these negative norm, negative energy states is the covariant conservation of the full T mu nu.
Right.
Okay, and that is, in the case of the E&M, that's just a divergence of J.
The trivial thing, right?
And so you can solve that by a fixed function of J.
Right.
But you cannot do that in gravity. So I would really like to know, like,
I'm going to impose exactly that. Yeah, I'll impose exactly that.
It has to be covariantly conserved for an arbitrary metric.
That's right. I'm going to impose that.
Okay.
Yeah. So the point is that I'm showing you what the source terms are in a particular gauge, and in that particular gauge, I can compute the constraints based on demanding in that gauge that the source term, this shadow T mu nu is covariantly conserved. But of course, that equation is is a Lorentz covariant equation. I can write that equation in any gauge. I'm just showing you what the form looks like for this source term in synchronous gauge. So this gives you, you see that it, like I say, it's almost time independent. P lower is a time independent function, but H time dependence depends on the divergence of the vector P. So I've chosen a gauge. I've told you what this source term is. I've required that that source term is covariantly conserved. That's automatics because what I've given you is the Gij equations only. And so I've just invented the G0I and the G00 equations by adding an arbitrary source term. But because the Bianchi identity relates the different components of the Einstein tensor, and because regular matter is expected to be covariantly conserved, that puts constraints on these functions.
So I'm totally confused, okay?
Okay.
Because you're telling me you're breaking gauge invariance, and you're going to tell me the equations only in a certain gauge.
Sorry.
You see why that's confusing? You've broken gauge invariance explicitly by introducing your functions, but you're only giving me the equations, quote unquote, in a particular gauge.
Yes.
Okay. So do you see why that's confusing? So in
Well,
other
I
words, well,
can,
here's my question.
yeah.
Can you write these equations in a way where you haven't chosen a gauge?
Yeah, so what I want to do is to define on a particular slice in this particular gauge some initial conditions as an allowed state of the theory. After that, I know that I have constraint equations, which are these from the covariant conservation of this extra source term. I can ask at that point, do those equations require any additional equations of motion? So normally if we put matter as a source term, we need additional equations of motion. And the answer turns out to be no. This completely fixes the evolution of this system in this particular gauge. After that, I can decide to go to any gauge, and in any other gauge, this T mu nu will have a different form in terms of these explicit functions. But I can write that T mu nu, hopefully I have it here. I can write that T mu nu as a covariant object. In other words, I can now make it something that's coordinate independent, and I can tell you what that function looks like uh, in something that's in terms of vectors and tensors that would live in the theory.
Because I mean, like I said, the question is not whether you have a predictive system of equations. Yes, you do. Congratulations, right? You do anything to the theory. It's a second order differential equation.
Yes,
Has initial conditions, you can solve it. Awesome.
sure.
Okay, but the thing is that if you generally what happens if you break gauge invariance, for example, you'll have plane wave solutions that carry arbitrarily large amounts of negative energy.
Sure.
Do you know whether you have those or not?
We do not have those. We do
How do
not
you
have
know?
any, we do not. We do not have any other dynamical fields of arbitrary energy.
No, you don't need additional fields to have these equations. Just if you add a random term in terms of the metric to Einstein's the Einstein-Hilbert Lagrangian, you'll get those terms. You'll get those solutions. Just
Yeah, we
add
do not.
something with a couple of derivatives and some random coefficients. You'll find those things.
Yes, we do not have any additional, we do not have any runaway solutions beyond the fact that gravity, of course, runs away, it expands forever, or can collapse, but we do not have any runaway solutions. We do not have any arbitrary negative solutions to these equations.
All right, I'd like to see that argument.
So in the case of, so let's just do the simplest case, which is let's set all the p's to 0 in this particular gauge. If we do that, we can rewrite this shadow T mu nu as some function, rho shadow times u mu u nu. So in other words, I can now rewrite this, and for this T mu nu to be covariantly conserved, it will have the form as some function of space over the square root of minus g. And this object is identical to how we construct a dark matter source or a pressureless dust in a frame. So I've chosen a frame, and then in that frame where u mu and u nu are this trivial function, which is basically the geodesic for the particles at rest, this T mu nu is a source term. This source term is exactly like the source term of regular dust. And regular dust itself, pressureless dust, does not have any other additional dynamical equations to define its evolution. So this source term is equivalent to that. And so any instability that you have in dust, you'll have here, but there are no additional solutions.
No, because
Yeah.
no, I think that if you have pressureless dust and it's some fixed function, okay, it's non-dynamical, right? Then you are going to have instabilities. You are going to
Very good.
create negative energies. And I don't think you've checked that because you've just looked at the Friedman equation and say, I like that solution.
No.
Not the one that has the runaway
This is
solution.
not the Friedman equation. This is not the Friedman equation.
So
This
you
is a
need
source. This is a source term which functionally is identical to a pressureless dust. A pressureless dust is in synchronous gauge. The pressureless dust is non-dynamical. It does not move. It's a static energy density. And in any other gauge, it evolves. And this source term does evolve in other coordinate systems. It collapses in the same way that dust does. There's no gradient term for this. It does it has the zero speed of sound in the same way that dust does, but it's identical to it.
Except that here, your rho is independent of P in synchronous gauge, right?
Well, it's not because that square root of minus g in principle has time dependence. But yeah,
how can this be covariantly conserved for any metric? You say it is, but I just have a hard time believing it. You're saying that you can just put in some classical functions and you get a tensor which is covariantly conserved for any metric. That sounds amazing to me.
Well, that T mu nu that I've written down is the form of pressureless dust. For some arbitrary
pressureless dust doesn't make it more plausible to me. Saying
No,
pressureless
what I'm
dust over
saying
and over again is not making it more. It's supposed to be a function of some classical function that you put in. I mean,
this is all classical, right? We're only talking about
Yeah.
classical equations. Yeah.
no, I know,
So-
but I mean by classical is non-dynamical. It's not obeying classical equations of motion. It's
That's
just a
right.
fixed function. That's
That's
what
right.
So you're
Yeah.
putting in a non-dynamical function
That's right.
and getting a T mu nu, which is covariantly conserved for any metric.
Yeah, if it's of this form, then yes. That's right.
Can you give what's an example? Like U mu is what? Is 1000?
U mu,
Rho SH. Can you give me the simplest possible example? U mu is 1000
yeah.
in
This is that's in a particular gauge, but what that
a
form rho u mu u nu, that form is a tensor, and if the u's follow the geodesic equation, satisfy the geodesic equation, then that is a covariantly conserved tensor. And there's some condition on the rho, but I can tell you what the condition on the rho is in synchronous gauge. It's that it's a function of space, not time, divided by the square root of minus g. But that is, yeah, I'm sorry to keep saying pressureless dust, but what I'm saying is that T mu nu and the fact and forcing it to be covariantly conserved, and part of that is requiring the u's to follow geodesics. that is a covariantly conserved source term, and you do not need any additional equations of motion. That's just happens to be a fact about a gas of particles that with no interactions.
Marcus, that's correct. Um,
So this, but the function, can you give me an example of this function? Like,
Yeah, I mean
this is not this thing can depend on X.
yes. So an example of the function in the frame where the u is 1, 0, 0, 0, example of the function is an arbitrary function of space divided by the square root of minus g. That function,
That's okay.
yeah, that renders
Arbitrary-
this
I'm
covariantly
asking
conserved.
Steve. Arbitrary function of X, pressureless dust, no problem.
um,
Depends on an arbitrary function of the space.
then it is covariantly conserved, provided that covariant conservation gives you two conditions. One is that the u's here, the velocities, are tangents to geodesics. That is that the time evolution of this dust is along geodesics.
For an arbitrary metric. Right?
It's going to be different for different metrics.
Yeah,
The u's,
but the function.
That's why there's a
has
square root of
nothing
minus g
depend-
there. Yeah.
There's only a square root minus g. Otherwise,
Okay,
it has
so
no other dependence on the
the
metric.
first condition is just a condition on the u's. The first condition is that the u's are
Geodesics,
geodesic.
which depends on the metric, not just on root g, depends on the whole
Yes.
details of the metric.
Right, so this, I'll come back to this in a second. This is related to my
So these
question.
u's here are they geodesics of the full metric, no matter what the metric is?
That's right.
That's
And-
my question. It's not obvious that in
Okay.
synchronous gauge that your world lines with t varying and your position coordinates fixed are necessarily geodesic.
Well,
That's-
these are geodesic. This is a special set of geodesics where I've set the velocity equal to 0. But these are geodesics in synchronous gauge. The covariant derivative of the square root of minus g produces the Christoffel symbol with the contracted indices that cancel the additional Christoffel symbol that comes out that's not 0 from the geodesic equation. So, I mean, you can check that this is just true, and then it's true for other metrics, meaning other coordinate systems, because in synchronous gauge, that's always u mu 1 0 0 0 is always a geodesic in synchronous gauge, because it's just the g00 that you've set to -1. So that's why the normalization is trivial there. If I go to some other metric, yes, then I'll have something that has to satisfy the geodesic equation, and it'll be a coordinate transformation of this system.
So Marcus, the second condition here, the second condition for covariant conservation is that the mass current is conserved. That is rho u mu.
Right.
It's covariantly conserved. And that is in synchronous gauge, that is equivalent to saying that rho is some arbitrary function of position over the square root of minus g.
Okay,
So that part's right.
okay.
I'm going to have to think about whether x equals constant world lines in synchronous gauge are necessarily geodesic.
So my claim about, so synchronous gauge does become sick at some point because there are coordinate singularities at crossings. And what I'll claim is that you'll have some initial arbitrary function like this, and that before the coordinate system goes singular, you can, of course, just like in regular GR, adapt to a different coordinate system and remove those coordinate singularities. The T, the energy density term, never goes singular in any coordinate system. But the problem is the definition of the metric is Steve, was exactly what you were saying. It's not well defined when you get crossings. But here we're now totally classical, and we have the source term, and we don't need any additional equations to describe how this evolves, and we can easily change coordinate systems. So my claim is that, and in some sense, it's like electromagnetism. Electromagnetism, I'm saying, oh, you can violate Gauss's law, but it's equivalent to just simply putting in a classical background, which is rigid and is not responding itself to electromagnetic fields. Here, we've put in a classical background, and it's not rigid in the same way, but it is something that only depends on the geodesic motion of the metric itself. So it doesn't require any additional dynamical equations, but it is equivalent to taking gravity, adding some matter, and that matter doesn't couple to anything else except gravity. It doesn't even couple to itself, and that matter just flows as a pressureless dust. So in that sense, we haven't done anything. We've added these source terms that are equivalent to adding a non-interacting sector coupling only to gravity, and of course, non-relativistic. Yeah, anyway, sorry, I actually did go through. Anyway, here's the algebra. It says that in fact, it does satisfy the covariant condition, and synchronous gauge is very nice because the Christoffel symbols are very simple, and a derivative of the square root of minus g is equal to the square root of minus g times a contracted Christoffel symbol. So that, in other words, if you started with a dust and you said it's a perfect fluid and you gave this form with p equal to 0, and then you asked in synchronous gauge what would be the form of this dust, and rho would just be a function of space over the square root of minus g. If you take the limit where pi is equal to 0 is what we've been taking, and if you take h of x greater than 0 everywhere, so it's positive, then you can do a spatial coordinate redefinition to make this source term even more simple, which is just a constant over the square root of minus g. And then you can perturb, you can ask for a metric which is slightly perturbed around the homogeneous case, and this source term now contains the same perturbation as the metric perturbation. And you can show that the effect on the source term behaves exactly like in linear order what a pressureless dust would do. So it really does evolve in the same way as a pressureless dust. And then even in this gauge, until geodesics cross, it looks just like the way dark matter would look. And if you do a gauge or coordinate redefinition, then you can get past those coordinate singularities. So we can also add perturbations around homogeneity, which is, I mean, of course, if you add a delta H, normally you could reabsorb that in the square root of minus g, but let's also add a tiny perturbation from the off-diagonal terms. So naively, with a homogeneous background, you can ask what do those source terms to the 0I equations do? And we discovered that those source terms actually redshift as 1 over a to the 5th. So they'll quickly redshift, even outside the horizon, these source terms disappear. This is like an additional vector which is disappearing. So that allows us to, of course, justify that we focus on the diagonal term. But these terms are interesting. And so if you want to ask what does that system with arbitrary vector pieces look like in any gauge? We can define in this gauge a particular additional vector, and then you can construct the shadow tensor T mu nu in terms of the geodesic motion u mu of the shadow matter, but then additional terms. And those additional terms are called a heat flux, which is not geodesic motion. It evolves densities from one place to another. And then that can be written in any coordinate system. Now, the crazy thing about these terms, so first of all, I don't know any particular type of matter for which you get these explicit heat flux terms, but there may be things that we can decouple from the rest of matter and behave exactly like that. We don't know of terms like that where you don't add additional pressure as well. But the other thing you can get, of course, is you can get crazier stuff, which is this source term. Maybe it's dark matter, or maybe it just is something weird. And weird could mean that it is positive in some places and negative in other places. And negative in other places would be mimicking negative mass particles. Of course, the matter is not there. This is just a configuration of the Coulomb part of the gravitational field. And in the early universe, if those off-diagonal terms are large, you could also, in principle, violate NEC, even with a positive diagonal term, but with large off-diagonal terms. And so this represent potential source terms that don't have any short distance instabilities, but maybe allow you to construct interesting cosmologies, bouncing cosmologies, or wormholes. And then the last thing I'll say is if you include electromagnetism and you put it in a general relativistic background, namely you put the shadow source term for the longitudinal part of the electric field in curved space, then you also find that that source term effectively redshifts as the universe expands, and it redshifts as if there's a charge density, maybe not surprisingly, that's classical and sprinkled everywhere. That charge density actually does follow geodesics, even though it does not respond to electromagnetic fields. So it would represent a weird kind of component of dark matter that carries charge, but is not responding to electromagnetic fields. And if you added such a term, you discover you would have to also add a term, shadow type terms, to the gravitational fields, and you find that they just modify the constraints on the H, the diagonal and off-diagonal terms for the source terms. But they're fully self-consistent and covariantly conserve both the charge density and this source term for gravity. So shadow matter is this game we're playing, and it's essentially the statement that we're going to start with a Hamiltonian and ask, are there consistent source terms that we can add, motivated by the fact that some of the equations are simply constraint equations. And these new source terms could be dark matter itself. There could be a fake charge component of dark matter. If there's a charge component, it could affect the CMB, BBN, galactic dynamics. Of course, we're looking to see if there's a simple way to solve the Hubble tension with the source term like that. It's equivalent to adding, say, very heavy charged particles that aren't deflected by electromagnetic fields. Since the new source terms could also violate the null energy condition in the same way, say, that Casimir violates the null energy condition without short distance instabilities, maybe there are new phenomena that are possible. All of this stuff goes away. You could say the problem of having to think about all of these things goes away with inflation because it can redshift all of this stuff. But if you would like this to explain dark matter, and I'm at least curious about it, and it's worth exploring, of course, new ideas for the initial condition. And the fact that we can violate NEC means that we can have interesting quasi-stable universes at early times that may decay into an expanding universe, and yet solve problems like the homogeneity. And that's it. Thanks.
Questions? Yep.
So, what about an old idea for initial conditions? Namely, you just choose them, which is kind of the spirit of what you're doing with these additional components, right?
Absolutely.
You're just choosing them, and there's never been an issue with choosing initial conditions that work for the universe, except people puzzle about whether they're tuned or.
That's right.
You could just take a stand and say, no, we're just doing old school physics. We're choosing our initial conditions.
Yeah, I mean, in a sense, it's the stand we take. I think I'm not saying inflation is compelling as a solution to the homogeneity problem necessarily, but it is a source of nearly flat perturbation spectrum. And so something we have speculated about is, can you get the right kind of noise, say thermal noise or 1 over F noise, in the system such that the perturbation spectrum would be nearly flat. And we do think that it's possible that if the universe was sort of in a steady state, maybe where Hubble on average was zeros, let's say it was oscillating, and then at some point it decayed into an expanding universe, then the noise associated with that system, it could be, was flat. And that those perturbations come from that noise. And so that would be it. Yeah. No, that's not in any paper. This is just an ongoing idea that requires hard work, and we have not completed it.
Go ahead.
So you mentioned tantalizing these possible impacts on the cosmological observations. Have you worked any of that through, or is it anyone?
We are working on it now. So we sort of yeah, with our postdoc Loris Del Grosso, he's found bounce solutions that are viable and end you up with a positive energy density at late times. So that we have some toy solutions that do that.
What about galactic dynamics or?
Very good. Yeah. So the thing that we're maybe interested most for galactic dynamics, and we're just starting to simulate these things, is if those P's redshift very fast, the off-diagonal terms, then for the smallest structures, they would be in principle the most important. And so the question is could you start looking at the smallest structures and ask, since this kind of violates geodesic motion, what would be the dynamics in bound objects due to these general heat flux terms? So we are looking to we are beginning to simulate exactly these things with the heat flux terms and see if there are qualitative differences in profiles or things like that. That we did a goofy thing, which was we took a gas of regular matter and we added a bunch of negative mass particles to it. And when you have different particles of different masses in a gravitational bound state, the different masses cause a sort of dynamical heating, which separates heavy particles from light particles. So we see that in what are they called? Globular clusters, where let's say 10 solar mass stars sink and 1 solar mass stars expand to the outer region due to these scattering of the heavy particles off of the light bath. And so similarly, you get something, if you add negative mass particles to a gas of positive mass particles, you get some kind of dynamical heating, but both the negative and positive mass particles expand. And so they dilute these systems. We don't, again, have a truly qualitative description of what we would expect, but it does present a way to essentially erase cores. So those are little toy simulations we're doing. But the things we're interested in most is, non-trivial cosmology, where you can get bound solutions or even oscillating solutions. This kind of stuff where you change the galactic dynamic structure. And then if you have a charge component that doesn't respond to electromagnetic fields, and let's say its initial conditions, perturbations, are similar to the initial conditions of just the normal dark matter perturbations, can those help contribute or change the dynamics of electrons after the CMB in such a way that maybe plus the radiation solves the Hubble tension? So that's a bit of a harder thing to set up. But those are the things we're exploring right now.
Well, in Newtonian gravity, if you have positive and negative mass, you get runaway solutions and just tie
That's right.
positive to negative mass particle. The positive mass will attract the negative mass. The negative mass will repel the positive mass. I
That's
think
right.
there are GR solutions that show that too. So doesn't negative mass give you that kind of instability?
Yeah, so we were looking for exactly that. But if you look, I mean, of course, if you have a gas of positive mass particles and you give them zero velocity, there's of course an instability, which is they collapse. And the thing that maintains the stability is, some angular momentum for each of the particles. And so what we wanted to know is, do you get that instability, or does angular momentum also save you in this case? And so the instability is a positive mass particle and negative mass particle, and they accelerate if they're equal masses. But in fact, for random initial conditions, that instability doesn't show up exactly because of angular momentum.
Okay.
Okay, let's thank David again.
Thank you.